Hey guys, welcome to Professor's Remake. In this part, we are looking into the ways to predict the collapse implosion of composites at extreme sea depths. In previous parts, I have explained the major factors associated with composite failure backed with science. If you have not gone through those, then it is highly recommended to go through them first. Just to summarize, composites at the extreme depths have to face many challenges such as extreme pressures, water absorption, ovalization, defects, delaminations, and fiber waviness. I have discussed about these in the previous parts. This video is based on the request by a subscriber who asked me to create a simple similar problem and show how FEA can predict collapse or implosion resistance while accounting for above factors. So let's dive into it. So I will try to keep mine and everyone else's life simple and create a very simple example analysis to investigate the effect of these factors, which I have mentioned in the previous slide and previous parts. Here you see a simple quarter cylinder made of composite material, and we are going to use this to investigate the effect of different factors. Dimensions and loadings are taken from actual Titan submersible to the best of my knowledge. We will do linear buckling analysis and see what pressure it will collapse at. Here I would mention that actual values are not important here, as these are just idealistic simulations. However, trends and effect of different factors would be the same for the case if actual full-scale simulations will be performed. If anyone is interested in full-scale model simulation, then please get in touch with your model and I will be more than happy to make a quick simulation tutorial in quick time. So let's dive into the ABAQUS software now. So here you see the part which I have already made. If you are not really familiar with how to make a simple 2D part, then I would strongly suggest to look at my tutorials on ABAQUS CAE. And this was the sketch. So I just drew quarter circle, and then joined them with lines. And then I pressed the done button and I got this part here. Okay, so this is how it's being made. For the properties, I have used the properties from literature. Again, I have many videos on composite materials, so I have used the similar properties there, so you can find the references in those videos. So the density I have used is this. Everything is in millimeters, so all the units are consistent with that. Elastic modulus, again, I'm using anisotropic properties, so I have defined Young's modulus in 3 directions, Poisson's ratios, and shear modulus in 3 directions for composite materials. Again, taken from literature. Machine damage parameters I have used are given here, which are not relevant at this point because this is just a linear buckling analysis. But again, you can find the references in my previous videos for on composites. And for damage evolution, again, this is not relevant, but these are the parameters I have used just in case if you want to go for non-linear buckling analysis for a full scale thing and you want to really see some damage. So these are the parameters I have used. I'm not going to do anything with this. Then what I do, I just go to sections, as you know, and then I create a section, which is solid section, and I will select the material. And in this case, you can see this is the section here, which has material 1, which I just created. Then the next part, I will assign the section. So I already have done that, and you can see it's material 1, which is assigned to this component. That's why it's green in color. So we have done with that. The another thing which is left is the orientation, since it's an anisotropic properties. So we have to really define the orientation and also give the apply and the stacking direction. So what you have to do, you have to press this material orientation button here, and then you have to select which component you have to really assign this, and then you use default, and then here you can go with this. I have selected discrete in this case, and then you can select what angle it has to rotate at, and also what is the stacking direction. So once you have done that, you press OK and you will see an orientation. So if I show you what I have done here is, you can see here I have used discrete. I have selected this object, and angle I'm using currently is -45. Again, I will show you later on by changing the angle, or even that is the orientation of the fibers, can change the collapse or implosion pressure. And I'm stacking in one direction, so stacking is in this direction, as you see. So this is how the local coordinates look like for this material. Again, you can play around with that, and you can have other better ways of doing it as well. And I'm not going to go into the details of that. You can look at my other composite videos on that. If I go to assembly, I just go and bring the part here. You have to press create instance, select the part, and it will be here. Then the step definition. So you can see I have Initial step, you can ignore this because you can also do dynamic explicit, but I haven't make it inactive. Rather, I have created a step which is linear perturbation buckling step. And if I go double click on it, then you can see I'm using default this, and I'm asking for only one value because we are looking for the first eigen mode, which will give us the pressure at which this will start to buckle, or rather that is collapse or implode. Rest is all default, so I'm not changing anything in this case here. And then I go to loads, which is more critical and important part. So firstly, let's see the boundary condition. So again, ignore step 2, which is explicit, but rather we just have one here. So you can see here I'm defining, if I go up, sorry, this one. So this one, since it's a whole circle and I'm only modeling quarter, so I have used X symmetric here. So this means similar thing is there on the other side. Similarly, for this part, I'm using Y symmetric because I can expect the same thing on the other side as well. It's a circular cylinder, and I use Y symmetric properties. In addition, since this can move in reality, but it's also constrained with the other part, so to avoid that motion and to create some kind of constraint, I am using an artificial constraint in real. So that's what I've done here. So I have fixed this point here in u1 direction and this point here as u2 direction to provide some resistance. Otherwise, you will have a free motion here and here in this direction, and next and here you will have free motion in y direction. So your collapse pressure or implosion pressure will be really low. And even now, we don't have any additional support. If it's a 3D structure and if it's connected to those titanium rings at the end, then obviously you will get some resistance there. And also in the thickness direction, you will have some material, so you will have resistance there as well. So this is more idealistic. This is uncertain in my opinion, and I could have used here at these 2 points where I am prescribing u1 and u2 to be 0. I could have used multi-point constraint and have a restricted motion here based on what is happening on the other side and along the thickness direction or longitudinal direction. So this is one uncertainty in the solution, and that's why I said these numbers are not 100% accurate, but they will give you kind of a qualitative trend in different things. So this is a loading, okay, and also I have to apply pressure, so that I'm applying external pressure, which is 40 megapascal, which is the depth at which it was there. If you remember, in one of the parts, I've given you the equation to compute the pressure at a certain depth of the sea. So based on that, it's around 40 megapascals. So I'm using 40. Just in case. Again, this doesn't matter here. You can also use 1 megapascal because this is just a linear buckling analysis. But in reality, it was like that. So this is done here. Meshing, again, I used, if you look at this, so I have used, in this case, a global size of 10, which is okay. It's a decent fine mesh, but you can again play around with that. Element type, if you look here, so you can see the element type should be plane stress elements in this case, although you can use plane strain as well, but I'm just going with plane stress to keep my life simple. Material, so plane strain would be a better approach. Okay, let's go and see how it runs. So we just created a job. Again, for creating a job, you just press this, name it. I always go with the full precision and then I press OK. So that's it. There I will just press submit. It will finish in quick time because it's just a linear buckling analysis for a 2D case. So now it's submitted. So now you can see it's completed in no time. And if I press results, I go to the visualization module, and if I press this, then you see the eigenvalue I'm getting is around 5.64 megapascals, which is pretty low. So it cannot go deeper into the sea with the current configuration, but in a 3D case with all the constraints correctly defined, you should get more realistic values. Now the first thing is the orientation of the fiber. Does it have any influence on this eigenvalue, which is right now the implosion pressure or collapse pressure for this structure? So if I go back to properties, and if I now change this orientation here, and let's say if I change it to 60 degrees, for example, so now the orientation has been changed. And now if I go back and run again, so 5.6, remember, was the last value. So let's see what it comes out to be now. So it's finished now. If I press results, And if I press this, then you can see now it has changed to approximately 2 megapascals. So even just changing the orientation of the fiber, which will change the orientation of the elastic moduli and all the material properties, changes everything for this case. So this is another very important parameter which you really have to keep an eye on when you are designing such kind of structures using composites. Okay, so now we have seen the effect of fiber orientation or orientation of the material, which changes everything. As you can see, implosion pressure or collapse pressure change almost to double. Now, next thing is basically to look at water absorption. So I already showed you in one of the parts that water absorption can decrease the strength of the material, and in some cases the stiffnesses as well. So obviously what I can do, if I change and go and change these properties and reduce them, then obviously I will get a lower value of that. So that's pretty trivial here, and we're not going to simulate that. It's an easy problem. You can do it by playing around with the numbers. If you already got the data that, okay, after how much exposure time in seawater, what are the properties at that point in the material, then you can use those, and that will give you the values. And you will see with the reduction in the properties or degradation in the material can cause reduction in the implosion pressure. Another thing was defects or porosities and delaminations. So you can have pores, you can have defects. So let's create some artificial defects in this material and see if they really influence your structure. So I will go and I will edit this structure. So I will create something like this. Then I will create a very thin defect. Something like a delamination. Now, if I regenerate, then you see I have created some kind of defect. In reality, delamination, as I showed you in my videos, looks something like according to the periphery, but let's say we have this kind of defect in the component now. So if I have to go back now, I have to remesh everything again. So if I mesh it again, I might need some finer mesh around this area. Yep. So you see there's a defect, and here it's almost fine. I mean, this doesn't look that bad, so I will just go with that. You can play around with the mesh again. You can use edge meshing and refine the mesh around the defect to get better results. So I'll go back, I'll submit to see what happens. So remember, it was 2.2 or something, case where we had no delamination or defects. This is the main idea. I mean, this is a thing, when you use a simple 2D problem, you can play around with different things, learn the stuff, and then you can go and apply it to the real life or actual complex problem. Otherwise, you do one change and you find out that it takes a long time to check, run the simulations. It's always good to simplify the problem, test everything, and then apply it to the real structure. So now if I go there, then you can see just having one defect has reduced the implosion pressure or collapse pressure from 2.2 to 1.3. And if I try to compute what is the difference, then it will be 2.02 minus 1.4 divided by 2.02. So it's around 30% change just because of one defect. And this was also reported, if you remember, in the part 5, where I discussed about different types of defects. They discussed about delamination defects, and they said that if they are more near to the outer surface, they are less sensitive in terms of their effect on the implosion pressure. But if they are near to the internal surface, they have a more significant impact on the implosion pressures. So as you see today, I have showed you the effect of extreme pressures, defects, or delamination, which could also change the implosion pressure, as well as the effect of fiber orientations or misalignments. In the next video, I will show you some stuff about ovalization. While if you are really interested in how to model the degradation, for example, due to water absorption, I have already given you some hints that you have to change manually the material properties to account for that. So I hope you learned something from this video, where I showed you how to model a simple linear buckling analysis to estimate the collapse or implosion pressure of a composite shell. And we tried to investigate the effect of extreme pressures. I gave you some hints on water absorption, related degradation, defects, delamination, and their effects on implosion pressure, and finally the fiber orientation effects. So if you want something more out of these, or you want to predict something through FEA, then please comment below and I will definitely help you out. If you have your 3D model and you really want to simulate an actual case, then send me that model and I can try to make a quick video on that as well. So hope by that time, until that time, enjoy the ride, and I will come back with some more interesting stuff in the near future. Bye for now.